In this lesson, we're going to discuss a new type of function known as a hyperbolic function. Hyperbolic functions share a great deal of similarity with trigonometric functions, in part because of how they are derived. The trigonometric functions can be obtained through many different ways, one of them being from a right triangle, the ratios of the lengths of two of the sides to one of in relation to one of the acute angles. Another way is from the unit circle, where we eventually realize that the unit circle comes about as a result of these triangles. The unit circle has an equation of x squared plus y squared is equal to 1. When an angle in standard position is drawn, the terminal side lands in a specific place and intercepts a point on the circle. There is a relationship then between the amount of rotation and the point on the circle. Another way to think of this is not just the amount of rotation, but depending on how far we rotate, we get an area, or we get a sector of the circle that has a given area. Rather than talk about the angle then, we can talk about the area of this region over which the angle rotates. In that case, as we know well, the x-coordinate of this point is the cosine and the y-coordinate is the sine. However, instead of defining them in terms of the angle measurement, I'm choosing to define them in terms of the area, which is directly related to the angle measurement. If we take that same approach, but with a slightly different equation, x squared minus y squared is equal to 1, that slight change in the equation produces a very different graph known as a hyperbola. The hyperbola observes two asymptotes. In this case, they are diagonal, specifically the diagonal lines y equals x and y equals negative x. Now, if you were to rotate this graph 45 degrees, you would see something quite familiar. In that case, it would look like the basic rational function 1 over x. However, when it is rotated in this way, it ceases to become a function, hence the implicit equation x squared minus y squared is equal to 1. But it does still have the same characteristics of two straight line asymptotes that are slanted rather than horizontal and vertical. Now, we can approach this in much the same way as the unit circle was approached, in terms of an angle in standard position whose terminal side is going to intercept a point on the curve, on the hyperbola. In this case, again, we can refer to not the measure of the angle, but the area of the region bound by the x-axis, the terminal side of the angle, and the hyperbola itself. Please note that we only need one side of the hyperbola for this. We can ignore the left side and only use the right side to define this. We could do it with the right side and the negative side of the x-axis, but we would end up producing the exact same situation. The nature of x squared and y squared both becoming positive upon squaring is such that it doesn't really matter which side of this we use, we're going to come out with the same situation. In this case, the ordered pair here is an x comma y, in a pair of values that would make the x squared minus y squared equal 1 true. So taking from the cosine and sine being the x and y coordinates, we're now going to call the x-coordinate cosine h, or hyperbolic cosine of a. And likewise, the y-coordinate will be sine h, or hyperbolic sine of a. At this point, it probably would be helpful to refer to the trigonometric functions as the trigonometric cosine, or the trigonometric sine, to differentiate them from the hyperbolic cosine and the hyperbolic sine. So in this way, we can define the hyperbolic cosine and the hyperbolic sine in a very similar way to what we saw in the trigonometric functions in the unit circle. In fact, this even readily extends to the tangent. The tangent is actually the slope of the terminal side, because if we take the y-coordinates and subtract them over the x-coordinates and subtract them, where the two endpoints are, of course, the origin and the point on the circle, then we simply get trigonometric sine over trigonometric cosine, which is the slope of the angled line. Well, this is no different in the hyperbolic function, because we still have a line segment with an endpoint at 0, 0, and on the other endpoint at hyperbolic cosine h, comma sine h. So again, if we were to take the slope of this, it would be the hyperbolic sine of h minus 0 over the hyperbolic cosine of a minus 0, which would give us the hyperbolic sine of a over the hyperbolic cosine of a. And why not then call this the hyperbolic tangent of a? Everything about it is the same in terms of this formula, except for those extra h's, signifying that these are hyperbolic functions. So the trigonometric functions and the hyperbolic functions have very, very similar properties. Each of the hyperbolic functions actually has an algebraic definition, as well as a definition based on the area with relation to the hyperbola. We're going to look at them one at a time. First is hyperbolic cosine. Now, considering the shape of the hyperbola and that the cosine, the hyperbolic cosine, refers to the x-coordinate, the values that the hyperbolic cosine can produce must always be greater than or equal to 1. On the other hand, it would seem that we could produce virtually any area you can imagine as our input. If we simply extend the endpoint further and further up the parabola, we get a very, very, very narrow but still infinite area if we progress far enough. So the domain of the hyperbolic cosine function is negative infinity to infinity, and the range is positive 1 inclusive to infinity. The actual algebraic definition of this is e to the x plus e to the negative x over 2. This produces a very particular graph. E to the x is an exponential growth function, while e to the negative x is an exponential decay function. Thus, when one of them is getting very, very large, the other is getting very, very small. So what we have here is that as x approaches positive infinity, e to the x plus e to the negative x over 2 is really going to approach simply e to the x over 2, because e to the negative x will approach 0. Of course, it will never actually reach 0, which means that this will never actually equal e to the x over 2, but it is asymptotic to e to the x over 2. Likewise, as x approaches negative infinity, now, on the left side, the decay function becomes very large, while the growth function becomes very, very small. The growth function will eventually approach 0, so that we have e to the negative x over 2. Again, it never exactly comes out to be e to the negative x over 2, but the graph will be asymptotic to e to the negative x over 2. So if we take a look at the graph of this, we're going to have, first, asymptotic, we're going to have asymptotes. So I'm going to put in a couple of spots here, because it is important that division by 2, that is a vertical distortion, it flattens the graph by a factor of 2, which means that our asymptotic functions are e to the x, and on the other side, e to the negative x. Going with the range of this function, the hyperbolic cosine has to be greater than or equal to 1. So the only place to draw it, observing the asymptotes, is in here, in almost parabolic type shape, but not exactly a parabola, because it is guided by the exponential functions, not by a parabola. This is the graph of hyperbolic cosine. The graphs of the other 5 hyperbolic functions, and yes, that includes the reciprocal functions, hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. The other 3 graphs are derived in similar fashion. Next, let's take a look at hyperbolic sine. Now, going back to, again, the graph of the hyperbola, from which we get our definition of hyperbolic sine, we can see that the y-coordinates extend downward forever and upward forever. So the range of the hyperbolic sine is all real numbers. Likewise, as with the hyperbolic cosine, this does extend to an infinite area, either above or below the x-axis. So we will also have domain all real numbers. So we're definitely going to get a different shaped graph here, if only because it has a different range than the hyperbolic cosine. As it turns out, the algebraic definition of hyperbolic sine is very, very similar to that of hyperbolic cosine, except this time the terms in the numerator are being subtracted. So, like before, as x approaches positive infinity, e to the x will approach infinity, and e to the negative x will approach 0. But because of the subtraction, this will approach e to the x over 2, but it will approach it from below. That's a distinction we hadn't made previously, but it is definitely necessary here. Because it is subtraction, we are subtracting a very tiny amount that gets tinier and tinier, but we're always subtracting. So we will always be just a little bit below the graph of e to the x. On the other hand, as x approaches in negative infinity, e to the x minus e to the negative x over 2 will actually approach negative e to the negative x over 2. Where again, on the left side, for large negative values, e to the x will drop towards 0, and negative e to the negative x will get larger and larger and become the governing, the controlling factor of this. So once again, we will be asymptotic to these two functions. Now that being said, note the subtraction has now become negative e to the negative x over 2. That gives us a vertical reflection. And that is being combined with e to the x, which is always positive, and therefore the graph of hyperbolic sine will always be slightly above the graph of negative e to the x over 2. So it will approach it from above. This matters because our asymptotic functions are going to be e to the x over 2 and e to the negative x. Sorry, negative e to the negative x over 2. Going to fix that a little bit. Thus, we must, on the right side, approach e to the x over 2 from below it, and on the left side, approach negative e to the negative x over 2 from just above it. And thus we get a graph that is something similar to a cubic function, although it is not flat in the center like a cubic function would be, but it has the same general shape. Of course, again, it is not guided by a cubic function. It is guided by exponential functions, so it definitely does not have a polynomial curve to it, but it does have the same general shape of being concave down on the left and being concave up on the right. There are 4 more hyperbolic functions. The 2 basic are hyperbolic sine and hyperbolic cosine, but we can, of course, have hyperbolic tangent. Hyperbolic tangent is, of course, as we already showed, the hyperbolic sine over the hyperbolic cosine. As such, it is subject to any domain restrictions that each of these have. However, both of them had a domain of all real numbers. Therefore, the hyperbolic tangent will also have a domain of all real numbers. Looking back to the hyperbola itself, we essentially are bound by an angle of pi over 4 and an angle of negative pi over 4. But remember, the hyperbolic functions are not defined by the angle, they're defined by the area of the region. Tangent is the slope, which means it can go as far downward tilting with a negative slope as far as a slope of -1, approaching it but never actually hitting it. Likewise, it can approach a positive slope of +1, but never actually get there. So the range of the hyperbolic function is going to be from -1 to 1, an open interval. We can never quite reach -1 slope or +1 slope, but we can be anywhere in between them. Now, taking the algebraic formulas we had for hyperbolic sine and hyperbolic cosine, hyperbolic tangent is going to start out looking quite awful, but once we realize that both of these fractions have the same denominator, that denominator can be eliminated and leave us with the numerator of hyperbolic sine in the top and the numerator of hyperbolic cosine in the bottom. Please note that this will, again, never quite be equal to 1, despite the fact that both terms start out with e to the x. As x goes to infinity, the numerator will always end up being ever so slightly smaller than the denominator, which will be ever so slightly bigger. As e to the negative x approaches 0, the numerator and denominator will approach e to the x over e to the x, which is 1, but it will never quite get there. The top will always be just a little bit smaller and the bottom just a little bit bigger, resulting in a fraction that is always less than 1. So again, as we go further and further to the right, e to the negative x in both the top and bottom will approach 0, but it will never actually reach 0, which means in the top we are always subtracting a teeny tiny bit, and in the denominator we're always adding a teeny tiny bit. So we will always end up with something that is just a tiny bit less than e to the x in the top, and just a tiny bit bigger than e to the x in the bottom, so that this will approach 1 from below. Likewise, as x approaches negative infinity, now again, these reverse their roles. So on the left side, e to the negative x is what controls this, and e to the positive x is what drops towards 0. Remember that the subtraction in the numerator applies to the e to the negative x. So we essentially have negative e to the negative x plus e to the x. And in the denominator, we have e to the negative x, positive e to the negative x plus e to the x. So as those e to the x's both approach 0, what we're left with in the top is negative e to the negative x and e to the negative x in the denominator. This time we will be approaching it from above. The graph then is going to have horizontal asymptotes at -1 on the left and +1 on the right. In between, the graph will have something of an x cubed shape, a cube root of x shape to it. Again, it is not exactly like that. In fact, if anything, this is more akin to the shape of an arctangent graph. However, the asymptotes are definitely not in the same place. The asymptotes here are at -1 and +1, whereas for the arctangent graph, they're at -π/2 and +π/2. The curvature in between is not exactly the same either, but it does have the same basic shape. It naturally follows, if we're going to talk about the reciprocal functions, to kind of talk about them in conjunction with the functions that they are the reciprocal of. So for hyperbolic cotangent, we're going to skip to that because we just talked about tangent. Cotangent is the reciprocal of tangent. Thus, we have f of x equals cotangent h of x, which would then be hyperbolic cosine over hyperbolic sine. Now, again, the domain of tangent, hyperbolic tangent, was all real numbers because the domains of the two component functions are -infinity to infinity. So that will be the same thing here. However, when hyperbolic sine was in top and hyperbolic cosine was in the bottom, our output values were stuck between -1 and +1, which meant they were always small. They were smaller in magnitude than 1. The reciprocal, therefore, will always be larger in magnitude than 1. So the range will exceed 1. On the negative side, it will exceed -1, and on the positive side, it will exceed +1. Again, not including them. If hyperbolic tangent was not allowed to be equal to 1 or -1, then its reciprocal certainly cannot be equal to 1 or -1. The algebraic form of this, then, I'm going to skip ahead a little bit now since we've already done the other three. We know how this is going to work. It is going to be e to the x plus e to the -x over e to the x minus e to the -x. And it's going to have exactly the opposite results from what we had from the hyperbolic tangent, or rather, I should say, it's going to have reciprocal results. In much the same way that the graph of trigonometric cotangent can be derived from the graph of trigonometric tangent, we can do that here as well. Now, we still, for our outputs, will only be able to approach 1 and -1. Now, to help us out, I'm going to sketch in the graph of hyperbolic tangent, because that will help give us a reference for what's going on with hyperbolic cotangent. The rule for reciprocals is, of course, that if a number is positive, then its reciprocal will be positive. Likewise, for negatives, reciprocating a number does not change its sign. So whenever hyperbolic tangent was positive, hyperbolic cotangent will also be positive. Likewise, when hyperbolic tangent is negative, hyperbolic cotangent will also be negative. The other rule is that the closer a value gets to 0, the closer its reciprocal will get to infinity. So I did misspeak up here before when I said that the domain of hyperbolic cotangent was -infinity to infinity. That's actually not true. Its domain is -infinity to 0 and then 0 to infinity, because at x equals 0, tangent is 0, and as a result, its reciprocal is undefined. So what we have here is that as tangent approaches x equals 0, it gets smaller and smaller and smaller, which means as cotangent approaches 0, it's going to get larger and larger and larger. As it comes down, since hyperbolic tangent is always a tad bit below 1, hyperbolic cotangent will always be just a little bit above 1. We're going to get the same symmetric shape in the bottom left. So that this, then, is the graph of hyperbolic cotangent. Next up is hyperbolic secant. Just as with trigonometric functions, hyperbolic secant, or secant h, is the reciprocal of hyperbolic cosine. Now again, hyperbolic cosine has a domain of all real numbers. But we do have to take into account whether or not hyperbolic cosine ever is equal to 0, because its reciprocal would then be undefined. So much like we did before, I'm going to sketch the graph of hyperbolic cosine down here. And again, it's going to have a similar shape to a parabola in that it is a U shape. So it never actually reaches 0. That's a good thing. That means that there are no places where we have to worry about the domain of hyperbolic secant. Since hyperbolic cosine is defined for all real numbers, and it's never actually equal to 0, we never have to worry about hyperbolic secant ever being undefined. Now, hyperbolic cosine, as we can see here, is restricted to an output value, or to an interval of outputs that is bigger than or equal to 1. Going back to what we talked about with reciprocals, if hyperbolic cosine is always positive, hyperbolic secant will also always be positive. But if hyperbolic cosine is always bigger than 1, then hyperbolic secant will always be smaller than 1, but still positive. Now, it will never actually reach an output value of 0, because to do so would require hyperbolic cosine to actually reach an output value of infinity, which it never actually does. It approaches infinity, which in turn means hyperbolic secant approaches 0. So the graph of hyperbolic secant is going to have a horizontal asymptote at y equals 0, and its graph will have to rise up to meet the hyperbolic cosine at 1, and then as hyperbolic cosine curves upward, hyperbolic secant will have to curve downward and approach its asymptote, and symmetrically on the other side. So that it actually ends up with a bell-shaped kind of curve. If any of you have done statistics, you would recognize a bell-shaped curve, and it has, again, a similar shape to that. The algebraic form of this is simply the reciprocal of the algebraic form of hyperbolic cosine. So it is 2 over e to the x plus e to the negative x. Last up then is hyperbolic cosecant. CSCH of x, which is 1 over sine h of x. Now, we do have to be careful here. Once again, I'm going to sketch the graph of hyperbolic sine to help us out. Hyperbolic sine had something of a shape, a similar shape to a cubic graph. And we do need to be careful then, because there is a place where hyperbolic sine achieves an output value of 0, which therefore means hyperbolic cosecant would approach infinity and be undefined at 0. So the domain of hyperbolic cosecant is everything except for 0. Likewise, the range must also be everything except for 0. Taking a look at this, as hyperbolic sine approaches 0 from both sides, hyperbolic cosecant will have to approach infinity. Positive when hyperbolic sine is above the axis, negative when hyperbolic sine is below the axis. But as we go further and further out to the side, hyperbolic sine will approach positive infinity on the right side, and as it approaches positive infinity, hyperbolic cosecant will have to approach 0. And symmetrically on the other side, coming from below the axis. Thus, the graph of hyperbolic cosecant looks very, very similar to that of the basic rational function 1 over x. Thus, the range would also be everything except for 0. The algebraic form of this would simply be the reciprocal of the algebraic form for hyperbolic sine. So that establishes the 6 hyperbolic functions and their graphs and their domain and range. We also have a number of hyperbolic identities akin to the trigonometric identities. There are, well, the word Pythagorean doesn't really apply here because the subtraction in the equation of the hyperbola prevents this from actually being in the form of the Pythagorean formula, the Pythagorean identity. But we can still do the substitution of hyperbolic cosine squared. Well, suppose we should use a different variable there. Minus hyperbolic sine squared is equal to 1. So while it is not technically accurate to call this a Pythagorean identity. It is the analogous set of identities to the Pythagorean identity. Just like with the trigonometric Pythagorean identities, we can divide both sides by hyperbolic cosine squared or by hyperbolic sine squared. If we divide both sides by hyperbolic cosine squared, then we have hyperbolic cosine squared over itself minus hyperbolic sine squared over hyperbolic cosine squared, also known as hyperbolic tangent squared. And on the other side, we would have 1 over hyperbolic cosine squared, or hyperbolic secant squared. Please note that these are the same two functions that are associated with each other in the Pythagorean identities for trigonometric functions. Tangent squared and secant squared appear in the same Pythagorean identity. Here they appear together in the same analogous identity. Likewise, we can take the original identity and divide both sides by hyperbolic sine squared, which would then give us hyperbolic cotangent squared minus 1 is equal to hyperbolic cosecant squared. There are other identities that are similar in how they work for both trigonometry and for the hyperbolic functions. For example, there is a trigonometric identity that says that the cosine squared of x is equal to 1 plus the cosine of 2x over 2. This also extends to hyperbolic functions. The square of hyperbolic cosine of x is equal to 1 plus the hyperbolic cosine of 2x over 2. Now, how can we be so certain of that? Believe it or not, it's actually easier to prove this identity for hyperbolic functions than it is for trigonometric functions, because the hyperbolic functions have algebraic forms that we can use. So to prove this identity, we can take the square of hyperbolic cosine of x and rewrite it as e to the x plus e to the negative x all over 2 squared. We can expand the top by squaring it, which will give us e to the x squared plus e to the x times e to the negative x plus e to the negative x times e to the x plus e to the negative x squared. And in the denominator, 2 squared is 4. Now, as it turns out, e to the x times e to the negative x is e to the 0, or simply 1. Over here, we have the exact same product. So we actually have, in simplifying this, we have e to the 2x by multiplying those exponents, plus e to the negative 2x, rearranging the terms of it, plus 1 plus another 1 is plus 2, and all of this is over 4. We can distribute the 4 in the denominator, and that gives us e to the 2x plus e to the negative 2x over 4 plus 2 over 4. We can extract a factor of 1/2 leaving us with e to the 2x plus e to the negative 2x over 2. And we can simplify the second fraction to 1/2. Thus we have e to the 2x plus e to the negative 2x over 2 is the formula for hyperbolic cosine with a 2x instead of just a plain x. Oh, excuse me, no. Squared. This is equivalent to 1 plus hyperbolic cosine of 2x over 2 if we were to rewrite the hyperbolic cosine of 2x times 1/2 as a fraction and then combine the numerators. So it is much easier to prove this identity for hyperbolic functions than it is for trigonometric functions. In much the same way, we can also show that not only is the hyperbolic cosine squared of x equal to 1 plus the hyperbolic cosine of 2x over 2, we can also, if we choose to, show that the hyperbolic sine squared of x is equal to 1 minus the hyperbolic cosine of 2x over 2. These formulas are identical to the trigonometric identities in structure. They just have h's attached to each of the trigonometric functions. There are similar analogous identities for the hyperbolic sine and cosine of a sum or difference of angles, as well as for double angles. So there are a lot of analogous identities, not all of which we're going to cover here. Now, an interesting thing, of course, is that if you go back and look at each of the graphs of the hyperbolic functions, you'll realize that some of them are 1-to-1, and for the few that are not, their domains can be restricted so that they are 1-to-1. And in that case, they become invertible. Yes, the hyperbolic functions have inverses as well. Now, trying to derive them is not really reasonable to do. The presence of x in multiple places, and not just in multiple places, but in exponents, makes it very difficult to solve the algebraic formulas for x in terms of y. Having an e to the x plus e to the negative x, the addition prevents us from simply using logarithms to pull the x's down out of the exponents. We could get one e to the power on each side, but we still have the y on the other side to deal with. And the whole idea is we need to get x by itself on one side, and that has to be the only instance of x. And that becomes very tricky to do. So we're going to omit the derivation of the algebraic formulas of the inverse hyperbolic functions. We will acknowledge that if we restrict the domain appropriately, that they are invertible, and we will simply give the definitions of them. The inverse hyperbolic sine, which has a similar notation to inverse sine for trigonometric functions. Now, when using inverse trigonometric functions, that notation with the -1 exponent, which isn't really an exponent, that is meant to signify inverse, we can get around that confusing notation by using arcsine. We cannot do that here because the interpretation of arcsine is unique to that of a circle. This is a hyperbola. That terminology of the length of the arc no longer applies here. So unfortunately, we have no choice but to use the inverse notation. The algebraic form of the inverse hyperbolic sine function is the natural logarithm of x plus the square root of x squared plus 1. Now, the inverse sine function, the hyperbolic sine function had a domain of all real numbers, and it had a range of all real numbers, and it was 1-to-1 on the whole thing. So if we interchange the domain and range for the inverse, they still are both all real numbers. On the other hand, in order to invert hyperbolic cosine, we need to restrict the domain of it. The domain of hyperbolic cosine has to be restricted to 0 to infinity, including the 0. That makes the range of the hyperbolic cosine function 0 to infinity. The range, however, remains 1 to infinity. So the domain of the inverse hyperbolic cosine will match the range of the regular hyperbolic cosine. And its algebraic form is going to be actually quite similar to that of the inverse hyperbolic sine, because again, the algebraic formulas for hyperbolic sine and hyperbolic cosine are very, very similar. The only difference here, actually, is that under the radical, we have a subtraction of 1 rather than an addition of 1. So we have a different domain, clearly. We have a very similar algebraic form that has one very important difference to it. Next up is inverse hyperbolic tangent. Now, if trying to find the inverse of hyperbolic sine or cosine is difficult, for hyperbolic tangent it will be even worse, because we have e to the x and e to the negative x both appearing in the top and both appearing in the bottom. So it would get even more complicated. Again, as such, we're going to omit that. The algebraic form of this is 1/2 times the natural log of 1 plus x over 1 minus x. The hyperbolic tangent function is 1-to-1. So there's no reason for any domain restrictions, and thus the range of the hyperbolic tangent becomes the domain of the inverse hyperbolic tangent. Inverse hyperbolic cotangent is also 1-to-1. Its formula is 1/2 times the natural logarithm of x plus 1 over x minus 1. Please note that while the addition in the numerator is reversible, the subtraction in the denominator is not. So that truly is the only place where these two inverse functions differ. Much like there was one small difference in the algebraic forms of the inverse hyperbolic sine and inverse hyperbolic cosine, there is a very slight difference in these two as well. Again, the hyperbolic cotangent is 1-to-1, so its range becomes the domain here. That is to say, everything exceeding 1 and negative 1. And now for the last two, inverse hyperbolic secant of x, which is equal to the natural logarithm of 1 plus the square root of 1 minus x squared all over x. Now, inverse hyperbolic secant is going to have a domain that matches the range of hyperbolic secant, which was only 0 to 1, open on the 0, closed on the 1. And lastly, inverse hyperbolic cosecant, which is going to have, again, a very similar formula to what we saw for inverse hyperbolic secant, with some minor changes. First of all, in this case, we're going to actually distribute the denominator of x, and there's a reason for that. Again, we're not getting into the algebra of the derivation of this, but we see our traditional kind of where we saw subtraction in one, we see addition in the other. So now instead of 1 minus x squared under the radical, it is 1 plus x squared under the radical. Now, here's why the denominator gets distributed. The denominator of the second fraction always has to be positive here. We didn't have to worry about that in the inverse hyperbolic secant because if you look at the domain of it, x was always going to be positive. Here we need to make sure of it because the domain of the inverse hyperbolic cosecant is the range of the regular hyperbolic cosecant, namely everything except for 0. So it is possible here to have negative x values, and in order to make it work the way it is supposed to work, we need to force the denominator underneath the radical to be positive. And again, we're not getting into the algebra behind the derivation here. We simply need to be aware of these formulas so that we can use them when necessary.